Okay, so now I want to just give you a final example on finding characteristic curves in PDEs, and now we want to focus on finding the characteristic curves in nonlinear PDEs. So far, whatever we talked about were mostly about linear PDEs, but characteristic curves could be not like just straight lines that we looked at in linear PDEs, and they can become nonlinear in the space-time diagram that you plot, and they can be much more complicated. So characteristics curves can become more complex in nonlinear PDEs. Okay, because of the nonlinear nature of that. And I want to solve an example on this so you get more familiar at how you can approach this kind of problems and why they are more complicated. Okay, so to do that, we start with Inviscid Burger's equation. So some of you who have fluid mechanics background might have heard about this equation. Inviscid means without viscosity. Inviscid Burger's equation. So let's see what it is. So the equation is partial u or partial t plus u partial x equals to 0. Okay, so as you see, this is a nonlinear equation because of this term, the second term here, right? Because we are multiplying u by u, so it becomes nonlinear, partial u over partial x. So I want to mention some notes about this equation. This looks like a simple equation, but it is nonlinear, and solving this could be pretty difficult. So I want to solve this equation using characteristic curves. Okay, so the first thing that we want to do is to find the characteristic curves in this example, or in this equation. Okay, so the question is find the characteristic curves in this Inviscid Burger's equation. So find the characteristics So I want to mention some notes before starting to solve this equation and finding characteristics. So one thing that you can see here is that this is similar to what equation? Advective transport equation that we talked about, right? At the beginning of the course. So similar to advective transport equation, but v equals to u here is variable, right? So there, if you remember, in the advective transport equation, what we had was partial u over partial t plus v partial u over partial x equals to 0, right? But here, there, v was a constant, okay? So we could set v as a constant, But here v is variable, so v here is u, right? So this is the main difference, that v is u, so it's going to vary, right, in the solution space. The second point is that this equation is kind of called baby, it's a baby Navier-Stokes equation. So people who know what is Navier-Stokes equation, it's the momentum equation for fluids. For example, when you solve based on the second law of Newton's second law for fluids, then you will get a Navier-Stokes equation. And the main term, the most difficult term in the Navier-Stokes equation, which makes it a nonlinear equation, is this term, partial u. If you have like a 1D flow, it would be something like this, partial u times partial u partial x. But in Navier-Stokes, because we have it's a three-dimensional equation, this will be in a vector form. Okay, so this is a baby Navier-Stokes equation, and it's mainly used in gas dynamics. When you have these shock waves and other things, aeronautical space, this is the main application of this equation. Then I want to talk about the initial condition. So initial condition for this the initial condition for this is given as ux and 0 equals to fx. So at ux and times 0, it's given as 0. And this equation does not have any specific boundary condition for minus infinity and infinity. Okay, so now this is the some notes about the Inviscid-Berger's equation. And now based on these, we want to find the characteristic curves for this equation, okay? And then solve it, given an initial condition, specific initial condition. Okay, so the answer, so as I said in the first note, this is similar to advective transport equation. So again, similar to first order advection equation, we can write partial u over partial t is, by using those difference definitions, is du over dt minus partial u over partial x times dx over dt. And so we just substitute this, in Berger's equation. Okay, so I'm going to substitute this into Berger's equation, and what I'm going to get, instead of partial u partial t, I'm going to get du over dt equals to dx over dt and I'm going to factor partial u over partial x minus u times partial u over partial x, right? So I have factored partial u over partial x and took this term to the right hand side of the equation and the other term also to the right hand side of the equation, and then I got this equation, okay? So from this equation, now it's easy to find the characteristic. So as you can see, dx over dt equals to u is gonna be characteristics here. This is the characteristics. So this is the characteristics for this equation, and as you can see, in order to see it better, you can see that along these characteristics, we can say when, that is when u equals to dx over dt, then du over dt is gonna be 0, right? So along these characteristics, du over dt is gonna be 0. So this means that u remains constant. So u remains constant along these characteristic lines that we found, characteristic curves that we found, okay? And this is actually the definition of these characteristics, right? You should, or your solution should remain constant along those curves, those characteristic curves. Okay, so this is, we answered the first question, that is finding the characteristics. And now the second question is that we want to answer: solve the Burger's equation given the initial data So given this initial data, the question wants us to solve and find the answers for Burger's equation, okay? So the initial data is given as, which is the fx, right? So here, as I said, the initial data, we can show it as fx is a general function of x, and here it is given in this problem as this. So 0 for x is smaller, less than 0. Ax for x between 0 and 1 over a and 1 for x greater or equal to 1 over a. Okay. So now the question wants us to find the solution for Burger's equation using this initial condition or initial data. So let's see what does this function look like. First thing first, let's just plot that. So if you have it here, so I'm gonna plot it with blue color. So less than 0, x can, let me just write it here before that. So this is the x and this is t. And I want to show, sorry, this is u or fx at x equals at x 0, at t equals to 0. So let me show this function. How does this look like? So when x is less than 0, u is 0, right? So this is going to be my line here. And when x is greater than 1 over a, so let's say if 1 over a is here, let's say it's here, and if this is 1, it's gonna be 1, right? So when x is greater than that, x, fx or u is gonna be 1 at time 0. So we have this here, and in between it's just ax. So I'm just gonna connect these two here. So this is how the initial condition looks like in my problem, right? So now with this initial condition, I want to find first the characteristics. I know the characteristics, but I want to plot them. And after plotting the characteristics, I want to find the solution for this equation, okay? So say from each point in space, so each point x, 0, and t in the initial condition, as you see, emerges a characteristic right? So from each point emerges a characteristic, and what is that characteristic? So the characteristic is dx over dt equals to u, right? So dx over dt equals to u. And so if you integrate this, this is going to give me x is ut plus x0, right? So from each point in the initial data, x0 and t, we have this line. So this line is gonna emerge from that characteristic, from that point in the initial data, okay? On which ux and the value of ux and t on this line is gonna be just a value at ux naught and 0, right? So this is just a this is the characteristic, right? So because the characteristic over the solution of u along the characteristic, which is this characteristic, should be constant, right? So that is the value of u, which is gonna equal to u at x 0 and t, and this is the value at ux and 0, right? So this is the initial data. Okay. And we see from this that each characteristic is a straight line but slopes may vary depending on the initial data, right? So each characteristic is a straight line, as you see here. So this is my characteristic, but its slope may vary depending on the initial data. So the slope here is what? Is this u, right? So the slope of this line depends on the initial data, and the initial data is u, x, 0, and 0. So this slope might vary. So let's now try to find these characteristics and then plot them. So, okay, I can say for x, 0 is less than 0, right? If your x0 is less than 0, your initial x at time equals to 0, then I can say that u at x and 0 is gonna be what? U at x and 0 is gonna be 0 if x0 is less than 0. So my characteristic, and I showed you this x characteristic, is gonna be based on this equation that I have here. Based on this equation, is gonna be ut plus x0, and u is 0, so it's gonna be 0 times t plus x0, so it's just gonna be x0, right? For the other limit, for x0 is greater than or equal to 1 over a, ux0 is gonna be what? Is gonna be 1, right? So the x characteristic, the characteristic curve for when x0 is greater than 1 is gonna be 1 times t plus x0, which is gonna be just t plus x0. And for in between, when x0 is between 0 and 1 over a, u at x and 0 is gonna be what? It's gonna be ax, right? So it's gonna be ax, and so the x characteristic, my characteristic curve for this condition when x0 is between these two is gonna be u times t, which is ax0 times t plus x0, right? So you see that my characteristic is always a straight line, but the slope varies. Slope here is going to be infinity. Here is going to be 1, and here is going to be ax0. So now let's plot it. Let's plot it, so I think then you will understand it better if I plot it. Okay. Okay. So now I want to write the characteristics and plot the characteristics. So this is gonna be my x, and this is gonna be t, x and t. So when x0 is less than 0, right? So I'm gonna first focus on this region, okay? When x0 is less than 0, then my ux is gonna be 0, and the characteristic is gonna be just x0, okay? So it's gonna look like something like this. If I plot it, it looks like this. And so these are the characteristics. So characteristic with xc is x naught, okay? And the value, so the value of x here, the value of u in this region is gonna be what? In this space, in this region, is gonna be 0 based on this. So it's gonna be 0. And now I want to go to the second limit, where say here we have 1 over a. So, and I want to look at the solutions here in this region when x is greater than 1 over a. So when x is greater than 1 over a, x naught, then the characteristic is going to be t plus x0. Okay, so it's just going to be a line with slope 1. So I'm going to just plot it. So for this region, I'm going to plot it with, say, purple. So this is a line with a slope 1. Then all of them are going to be similar. A line with a slope 1, right? So the characteristic here, so for this one, let's say, the characteristic for this one is gonna be t plus 1 over a, right? Because x naught here is 1 over a. So this is the equation for this line, and the other ones are going to be xc, the characteristic is t plus x naught. So depending on the x0 here, this is going to be the characteristic, and the solution, ux and t in this region, in this purple region, is going to be 1, right? Here it is. It's going to be 1. So let me just make this with blue to be consistent. So here ux and t is 0. Okay, and the third region is in between these two. And what's going to happen? So the thing is, we said characteristic is a straight line, but slopes may vary depending on the initial data, right? So the slopes here are going to vary because depending on the initial data, because my slope is ax0, right? So when x0 is 0, this is gonna be 0, and when it is 1 over a, slope is gonna be this line, right? 1. I mean, in between, it's gonna just vary from this infinity slope here and here, the infinity to this. So it's gonna be something like this, right? So let me just draw it. So it's gonna be let me draw it with another color. Okay, so this is gonna be varying over this, and this region, we call this region as expansion fan. Expansion function. So expansion function, and this, the characteristic here is gonna be ax0t plus x0, right? And the solution ux and t, we don't know. We have to find. So what is the solution here? The solution here is given as ax, right? But I want to find it as for ax is just for when it is 0. So it's gonna be when time is 0, right? So here I know the solution. So the solution is ax 0. But then I want to see what happens as we propagate in time. So the question is, what is this in terms of x and t? Okay, so let's answer this question. So say we have a line here, and this is x and this is t. Okay. And I want to represent, and I want to find the solution here. I want to find the solution here. So here say is x and t, and here is gonna be x0. So I know that I know two things here. First, I know that u at x and t is gonna be ax0, right? This is based on what fact? The fact that this is a characteristic curve, and it's gonna just propagate, the u is going to be constant here, and u here, I know, u at here is ax0, right? So u x0 and t is ax0. This is based on here. Okay. And this is just going to propagate that solution. So I know the u based in terms of x0. And I want to find it in terms of x and t. And the second thing I know that this is because this is a characteristic curve. I know the equation for this characteristic curve from here. So the equation is going to be ax0 t plus x0. So I have these two equations. These are the known things, and I want to find uxt from here. So I want to replace this x0 here from this equation to find a relation only based on x and t. So this equation is going to give me, if I factor out x naught in the right hand side, I'm going to get x naught at plus 1, right? And so I can say x0 is x over at plus 1. So now I just substitute this here. And what I get is this. I'm going to get ux and t is ax0 equals to ax over at plus 1. So I found the solution here. And so this completes the full solution space of this equation, this Berger's equation, based on the given initial data. So let me write it down. So ux and t is going to be 0 when x is less than or equal to 0. It's going to be ax over at plus 1 when x is between 0 and 1 over a plus t. And it's going to be 1 when x is greater or equal to here, right? 1 over a plus t. And this 1 over a plus t is just this line here. It's just this line. So this is going to be 3 regions. So, right? So the first region is this one. Let me start it right. The first region is this region. The second region is here. This region by this, which is defined by this characteristic line here. And then the third one is this region, again defined by this characteristic line, where u is going to be 1 here. Okay, so we have these 3 regions. Okay, so this is going to be the final solution for this problem. Okay. So this is the Berger's equation with the given initial data that we had. This is going to be the solution for that. And now, just to make sure this is correct, let's see, check if this satisfies the PDE, the Berger's equation. So let's see. So the PDE we had, it was partial u over partial t plus u partial u over partial x equals to 0. So for x less than 0, this is gonna, u is gonna be 0, right? So, and du partial u over partial t is gonna be also 0, so this is gonna satisfy that. For x greater than 1 over a, u is gonna be always 1, so partial u over partial t is gonna be 0. There is no change in time, and also there is no change in space in x. So this is gonna be 0, and this is gonna also satisfy Berger's equation. And in between, when x is between 0 and 1 over a, sorry, this is 1 over a plus t. Let me correct it. 1 over a plus t, and this is also 1 over a plus t, then u is gonna be ax over at plus 1. So let's see if this satisfies also the Berger's equation. So partial u, partial t is gonna be, if you take the derivative with respect to time, you are gonna get minus a times ax over at plus 1. And let's take the let's compute the second term, which is u times partial u over partial x. So it's gonna be ax over at plus 1 multiplied by partial u over partial x. So it's just a over at plus 1, right? So we are gonna get a square x over at plus 1 square. And so if you sum these two terms, they are gonna cancel out, right? They are just the same, but with different sign. Let's see. So this is this term, and the second one is this term. So they are just the same, but with different sign. So I made a mistake here. Sorry. This, we have a square here. Because if you take the derivative, this is how it works with respect to time. So we are gonna have, so this term and this term are gonna cancel out when you sum them together. So this also satisfies Berger's equation. And so this solution is a valid solution and for this Berger's equation. So let me just quickly, briefly review what we did in this session. So we looked at characteristic curves in nonlinear PDEs. Okay, so in nonlinear PDEs, characteristic curves, characteristic could be much more complex than linear PDEs. So here we only looked at an example where, again, the characteristic were straight lines, but as you can imagine, the characteristics can also vary, right? So they can be even curved lines. So depending on the nature of the equation that you are solving. So we gave an example with Berger's equation where we change is similar to advective transport equation, but we just change u, the v to u, and then it became a nonlinear equation. And then we tried to solve this equation with a given initial data just for this shape. And I just note that if your initial data is different, your characteristics are going to be also look different. So this is not a general case. This depends on your initial condition. Okay, so this is not really a general graph. Completely depends on your initial condition. And it could be much more different. And this we found for this initial condition that was given here. This is the characteristics that we found. And we are going to have three regimes based on this definition that we have and we gave here. So we are going to have three regimes. When x is less than 0, u is going to be 0. When x is greater than this line, t plus 1 over a, the u is going to be 1. And in between, we wanted to find it. So you see that the characteristics are going to just increase, so the slope is changing. And then we found this characteristic based on the given information in the problem. And finally, we checked that whether this solution that we found is just a final check and double check if it satisfies the original PDE, which it does. So this is a solution, one solution of Berger equation, just one solution, which depends on the initial condition. And I just want to note, if you have, you can have much more difficult cases in which, for example, your initial condition is going to be different. So like the other side, instead of this way, it can be like this way. And then your solution is going to be, your characteristics are going to be also different. So they can be, they can look like something like this. And then you will have a shock, like somewhere where all the characteristics are gonna gather and they're gonna touch each other. So for one location where a lot of characteristics are gonna come there from different initial data, and this is in gas dynamics. This is where a shock happens, right? So this has a lot of implications for these gas dynamics problems. You can have a shock here, a shock wave, which depends on the way that the initial conditions work. And so this is very important for these transonic and subsonic kind of problems in gas dynamics and kind of in general in aerospace problems. This becomes a very important equation. Okay, so this was just to give you an idea of nonlinear PDEs and how the characteristics can be used to solve these PDEs, nonlinear PDEs. And in the next lecture, I'm gonna start storm level problems and show you another way of solving PDEs, which is by separation of variables. After that, we're going to go through complex Fourier transforms. And after that, we're going to finish the analytical part, and we're going to start the numerical part where we will look at finite difference and hopefully finite volume methods. Thank you very much, everyone.